One of the more common mistakes that I see for the quotient rule is almost like an overuse of the quotient rule. For example, when you have a constant or a monomial in the denominator, the quotient rule is unnecessary. The first thing you're going to do is rewrite. So you always double check, because when people see a fraction, they're like, oh, the quotient rule. Does the quotient rule work? Absolutely, but the likelihood of you making a mistake increases by a lot. So you're making the problem more difficult for yourself than you have to. So instead, when you see a monomial, like the examples that I have down here, every single one of them has either a constant or some form of monomial in the denominator. Then a quotient rule is not necessary. So I want you to just be careful with that and keep that in mind. When also later on, when we get into the chain rule, when you have a constant in the numerator, not a monomial, but a constant in the numerator, you are better off just using the different methods instead of overusing the quotient rule. Okay, so what do we see here? Well, each of these we're going to rewrite instead. So I see that it's a constant in the denominator. I'm going to rewrite this as y is equal to 1/8 x to the third plus 5/8 x. And then just use the power rule. So the derivative dy dx, or y prime, is going to be equal to 3/8 x to the second minus, no, plus, sorry, 5/8. I wrote the right thing. I said the wrong thing. Same for the next one. Rewrite f of x before I take the derivative, 9/8 x to the third, and then just use the power rule. So we get f prime of x is equal to 27/8 x squared. And you can even be fancy and put the x in the numerator if you wanted to. So in this case, 27x squared over 8. Same up here. Both of them have a common denominator, so I could rewrite this as 3x squared plus 5 over 8, but you don't have to. The next one, again, it has a monomial in the denominator. So even though it looks very complicated, I would then do a little bit, believe it or not, it's simpler to distribute the 2 and then divide each term by 3x. So I would rewrite this as y is equal to -2 times 4 is -8x divided by 3 over x. The x's cancel out, and I get -8/3. And then the -2 distributed gives me +16. So that's definitely a plus. 16x to the third over 3 x to the first gives me 16/3 x squared when I rewrite that, and then just use the power rule. So y prime in this case is equal to the derivative of constant is just 0, so that drops out, and I end up with 32/3 x. Sorry, my handwriting is really bad, so let's try that 3 again. 32/3 x. Same for the next one. Just keep in mind that the denominator is a monomial. I could rewrite that as 8x to the 1/2 and then make that go into each term. So I'm going to rewrite that g of x. I'm going to get 6 over 8 is reducing to 3/4. And then x squared over x to the 1/2, when you subtract the exponents, gives me x to the 3/2. And then minus, I get -4 over 8, that's 1/2. And then x to the first minus 1/2, so x to the 1/2. And then the last one is going to be plus 5/8 x to the -1/2. I'm just bringing that up. And then use the power rule. So g prime of x is going to equal, what do we get? 9/8. 9/8 x subtract 1 gives me 1/2. And then minus 1/2 times 1/2 is 1/4 x to the -1/2. And then plus, no, I guess that would be a minus here. Minus, and then we get 5/16 x to the -3/2. And you're fine, you can leave it. That's it. You just took the derivative. All right, a couple of things. First of all, technically we haven't proven when it's not an integer, that we can use the power rule when it's not an integer or when it's negative. So one of the things now with the quotient rule that we can prove is that when we have a negative integer as an exponent, the power rule also works. So that's something I promised you when we did the power rule before that we would do as we went along, prove all the parts of it. If n, so here, for the proof for this here is if n is a negative integer, then there exists a positive value k such that n is equal to negative k. So in other words, this here would be negative k. If I have n is equal to n, or x to the n is equal to x to the negative k, then I hope you will agree that you could rewrite x to the negative k as 1 over x to the k. And then you're going to apply the quotient rule. So apply quotient rule just to explain what we're doing. So here, the derivative here becomes then ho, which is x to the 6th, d high, so the derivative of the higher one is 0 because it's a constant, minus high, which is 1, d ho, oh, I have to use the power rule because now it is a positive integer down here. When I moved k down, it became positive. So k times x to the k minus 1 all over x, so draw the line and square below, right? So ho d high minus high d ho, draw the line and square below, is then going to equal, let's simplify, the first term becomes 0. In the numerator, I get negative k x to the k minus 1 over x to the 2k, a power to a power we multiply. And then, oh, look, they have the same base. I can subtract. So I get negative k x to the k minus 1 minus 2k. Because they both have, just to clarify, this and this is the same base. So we can just subtract the exponents. So that is going to equal negative k x to the negative something, negative k minus 1. But since negative k is defined as n, we did that up here at the top, right there highlighted in pink, I can use substitution. So by substituting back in, I can see, okay, negative k is n, and x to the negative k is n minus 1. Oh, wait, that's the regular old power rule we knew before. So what that means is that it also works. So power rule also works when power is a negative integer, like so, like that.